Hi everyone, I'm Ruoxu talking about minimum cuts in directed graphs via partial sparsification. Joint work with Jason Lee, Danupon, Nanongkai, Debmalya, Panigrahi, Quanrud, and Thatchaphol, Saranurak. We consider the classical problem of finding the minimum cut in a weighted directed graph. Recall a cut in a directed graph is defined to be a bipartition of vertices into two non-empty sets, that is source side S and sink side T. And its value is the total weight of edges from S to T. So in this example, the minimum cut value is 1 because in the marked red cut, there is only one edge from S to T. Although there are 3 edges from T to S, we don't count them. Okay, so our problem will be find a cut with minimum value. Or equivalently, it is the minimum number of edges whose removal creates multiple strongly connected components. We can also define other versions of minimum cuts. So first, a minimum S cut is defined to be the min cut with a given vertex S in the source side. So in this, again, in this graph, if we fix this node to be S, then the minimum S cut will be another cut, also with value 1. And then the minimum ST cut is min cut with a given vertex S in the source side and T in the sink side. So again, in this graph, if we mark S and T in this way, then the ST min cut will have value 2. Okay, it's known that minimum ST cut is equivalent to ST max flow. And these variations are closely related. So first we can solve minimum cut using 2 minimum S cut calls. To do this, we first fix any vertex S and find the minimum S cut in G as well as the edge reversed graph and return the smaller one. If the min cut has S in the source side, then we can find it by minimum S cut. So if S in the sink side, then we can find min cut in the edge reversed graph. And also we can solve minimum S cut using n-1 minimum ST cut calls. That is simply run minimum ST cut for all other vertices T and return the minimum. So these reductions are simple, and in this paper we aim to get a stronger reduction, that is solve minimum cut or minimum S cut using square root of n minimum ST cut calls. So this will produce the efficient algorithm. Now let's see some results. We have just discussed that minimum cut can be solved using n max flows, and using the current best max flow algorithm, this will give us a baseline of mn plus n to 2.5 running time. And the previous best algorithm is nmm time, so slightly better than the baseline. Date back to Howarding 1992. And before Howarding, there are also other MN running time algorithms on simple graphs. In contrast, for undirected graphs, min cut can be solved in near linear time, so much better, and even faster than ST min cut. So in this paper, we shrink the gap a little bit by solving minimum S cut or the minimum cut using root n minimum ST cut calls. And our actual reduction is slightly better than root n max flow calls. So using this final parameter, our runtime will be O tilde nm to 2/3 plus n squared, where O tilde hides Poilov factors. Our algorithm is Monte Carlo, meaning it is a random algorithm that has a small probability to fail. In contrast, the Howarding algorithm is deterministic. As a final remark, if we assume the max flow can be solved in near linear time, ideally, then our runtime will improve to a minimum of nm to 2/3 and m times root n, which is slightly better. We have just shown that for a direct min cut problem, we can solve it in at least n square time, right? And it will be larger than n square for dense quarks. But if we allow approximation, then the running time can be improved to n squared. So this is also our new result. So improved to near quadratic time. And we also consider the minimum vertex cut. So vertex cut is a tripartition LXR of vertices. So intuitively, if we cut the vertices in X, then there will be no edge from L to R. And this approximate version of minimum vertex cut can also be solved in near quadratic time. And previously, for both these approximate problems, no improvement was known over the exact algorithms. That is, MN exact algorithms are the best for both problems. In this talk, I will only focus on the exact algorithm for direct min-cut problems. So our algorithm will divide two cases, and the easy case will be when the cut is balanced. That is, both sides have at least k versus for some parameter k, which is roughly root n. So in this case, we just sample log n over k terminals. Then with high probability, there are terminals on both sides of the min cut. So if we run st max flow from S to all terminal t and return the smallest one, then it will be and then we can find the min cut because the terminals, there is a one terminal on the other side that says, so the min cut will be found by the st cut over ts min cut. Okay, so the hard case is when the cut is unbalanced. That is, one side has less than k vertices and hard to hit by some sampling. And we can assume the small side is the sink side. So in this case, our algorithm will perform 3 steps. First, we sample edges to reduce the min cut value to O tilde k. And also, we preserve the min cut to be 1 plus O epsilon approximate min cut. So this is called partial sparsification. And secondly, we will pack about k edge disjoint arborescences or directed spanning trees to make the min cut has 1 plus O epsilon edges on average in each arborescence. And finally, we will find the smallest cut in G that has exactly 1 edge in an arborescence. So such a cut is called the one-respecting arborescence. And we will run this step on polylog random arborescences. So our claim is that the smallest cut return is the min cut with high probability. Next, I will explain these 3 steps. So first, by sparsification, we mean we want to reduce number of edges while preserving the cut information in some way. So note that we assume the sink side has less than k vertices. So there are only n choose k such cuts. Okay, so this enables us to bound the total failure probability that we can approximate them using trend bounds. So we'll sample each edge with probability about k over lambda, where lambda is the min cut value. Then the unbalanced cuts will be approximately preserved. Okay. So we can approximate every cut using Charles bound. So using Charles bound to bound the failure probability that some cut is not approximated. And then because there are only polynomially many unbalanced cuts, we can use a unit bound to claim that the total failure probability is small. So all cuts are preserved. And for balanced cuts, they might be much smaller. So they cannot be preserved because they are exponentially many. But that's bad because that will we will lose the information of min cut. So we want to modify the graph to make all balanced cuts much larger without changing unbalanced cuts significantly. And we do this simply by adding a star from this. So after that, in our resulting graph, our min cut value will be reduced to O tilde k by the sampling. And also our original min cut in G is now an 1 plus O epsilon approximate min cut, because the unbalanced cuts are still approximated and the balanced cuts are raised above the min cut value. And after the sampling, we can now contract all nodes with more than O tilde k in edges. This does not affect the min cut because we claim all the nodes we contract is in the source side. For a node in the sink side, the number of edges from T star is the most k because the T star has size k, and number of edges from source side is the most O tilde k because the cut value is O tilde. Okay, so such an edge cannot have too many in edges. So the node in the sink side cannot have too many in edges. So after this contraction step, the edge size is also reduced to O tilde nk. Of course, M will be a trivial buffer bond. Okay. The runtime of this sparsification step is near linear because we just do some sampling and degree check. So it's near linear. The next, in arborescence packing, we find a maximum edge disjoint collection of spanning out trees rooted at S. And we will do this in the graph H from prior sparsification. Okay. So we know from linear programming duality that the maximum number of arborescences we can pack is equal to the value of minimum S cut lambda H. And we also know using multiplicative weight update, we can get an approximate solution of the arborescence packing problem. That is, we can get a arborescence packing with value 1 minus epsilon lambda H. And runtime will be mh times lambda H, which has already been reduced to mk or nh squared. So what we have now is that the min cut is now approximate min cut in H, so has 1 plus O epsilon lambda H edges, while the packing has 1 minus O epsilon lambda H arborescences. Therefore, a randomly chosen arborescence will have 1 plus O epsilon edges from the min cut in expectation. Then, if we then we also notice that since an arborescence is like a spanning tree, it must use at least one edge from the min cut. Okay, so if we pick random log n random arborescence from the packing, then with high probability, at least one of them will only use one min cut edge. So such a tree is called one respecting tree. So we only need to solve, given an arborescence X, find the smallest S cut in G that intersects S in exactly one edge. And we will run this on log n randomly chosen arborescences, and the smallest return cut will be the min cut with high probability. Note that although only one edge is from source side to sink side, there can be many tree edges from sink side to source side. Okay, so the structure is not too simple, and the dynamic programming doesn't seem to work. Nevertheless, we can exploit the structure using the following observation. For any vertex U in the source side, after deleting U on the tree, sink side is entirely contained in one connected component. So the connected component of the tree after removing U. So we prove by contradiction. Assume there are two components that contain some sink side nodes. Then, because used in the source side from the tree path on the tree path from source side to sink side, there must be a cut edge. So the two tree passes will contain two cut edges, which contradicts the assumption that the tree has only one cut edge. So we can use this observation to design a divide and conquer algorithm. We'll pick the centroid of tree and recall that centroid means removing it will produce components with at most a half in size. So if there are two possible cases, if the centroid U is in the sink side, then the min cut is given by the SU min cut. If U is in the source side, then by the previous observation, our sink side is totally contained in one of the components of the tree after removing U. So we can do contraction. So we can solve them recursively. So the algorithm will be choose a centroid, find the SU min cut, and then recurse on each component of the tree after removing U, while contracting other components, all other components to S. Because in this case, in the case that the sink side containing one component, other components are in the source side, when I return them smallest cut. And the correctness it follows from our analysis of two possible cases. Next is bound running time. First, the recursion depth is log n because we always partition the tree using centroid. But the total size of graphs in any layer of recursion can be large due to repeated edges. So our solution will be we modify the recursive graphs so that we can run all calls in the same recursive layer in parallel. So the overall run time will be log n maximum calls. So how do we run the recursive calls in parallel? In this figure, assume the rectangles are different components and we want to run a mixed flow from S to the centroid of each component. Although there can be cross-component edges, since other components in the subproblems are contracted to the source, we can always replace such UV edge by SV, and without changing the nature of our mixed flow run calls. So now all the components are independent mixed flow subgraphs, and we can run them in parallel by adding a supersync and link all things to the supersync. In conclusion, our overrunning time will be, for balanced case, we run N over K mixed flows. And in unbalanced case, the bottleneck is arborescence packing. So if we pick K to be M to the 1/3 plus root N, then the total running time will be O tilde NM 2/3 plus N squared as claimed. Finally, I'd like to discuss some open problems. First, can we further improve the runtime of directed min cut? In particular, our bottleneck is not the final step of unrespecting min cut, which only takes polylog max flows. Can we improve it to be comparable to parallel max flows? And secondly, can this result be generalized to other min cut problems in directed graphs, including all pair connectivity, Steiner cut, single source all sink connectivity, and all pair symmetric connectivity? So for all these problems, no better algorithm was known than running N max flows. And although all pair connectivity has a strong conditional lower bound, other problems don't have a strong lower bound yet. And finally, there are other applications of our partial sparsification technique or respecting directed min cut algorithm. Okay, that's all. Thank you.